So without further ado, it's a pleasure to announce the next speaker. So we'll have Lorenz Eberhard from IAS speaking on string correlators on ADS3.
Thanks very much. Let me start by thanking the organizers for organizing this very exciting conference in these very interesting times. Today I will talk about some correlators on string correlators on ADS3. And the talk is based on a paper I put on the archive a couple of weeks ago with Andrea Day, and also work in progress with him. Okay, so we already heard some talks about string theory on flat space in this conference, but I think string theory, especially on ADS, is very important and interesting because we want to ultimately understand holography. That's at least my physics motivation. Before going on, I should say maybe that, of course, I'm a physicist, but something happened in this project that never happened to me. Namely, we started with some physical problem, and then in the end, there was some sort of pure math output of it. So even if you're not interested in the physics, and I try to explain to you the physics and the math behind it, but there's some interesting math results that come out of it. So the simplest setup we can study is ADS3 target space, because ADS3 in the language of physics can be supported by pure NS flux or a B field. And if we have such a situation, then we can study the string via perturbative string theory. And the worldsheet theory is now not just like 10 free fermions and bosons and the RNS formalism say, but it's some more complicated worldsheet theory in the form of the SL2R WZW model. The SL2R here originates just from the fact that ADS3 as a manifold is nothing else than SL2R. Strictly speaking, the universal cover of SL2R, but it has become sort of convention to abuse notation here. So this is the worldsheet model I want to talk about today. And many of you, I suspect, know about the SU2WZW model, for instance, and this is like a non-compact cousin of it. And it has been suspected to be solvable for a long time, but so far it's not really achieved. So there are some parts of it that are solved and so on, but there's no full solution of this non-compact WZW model. So why is that so difficult? Why is it so much more difficult than the compact case? And the main reason is that there is some phenomenon that is called spectral flow. So I will first explain you in physics terms what spectral flow is. So in this picture here, this is supposed to represent ADS3, so the sort of ball, or rather it's Euclidean continuation. So this is nothing else than hyperbolic 3 space, which we all know is some ball with the hyperbolic metric. Inside this hyperbolic 3 space, we have some string worldsheet, which I drew here in this color. And so you see already that this worldsheet is sort of strange, and you're not used to it from flat space. If you're a flat space person, then you usually study some string correlator that is like, say, a Riemann sphere with 4 punctures, and there are sort of external vertex, external string states, and there's scatter, and the worldsheet is just a 4-punctured sphere. Similarly here, if you stare at this picture for a long time, you can convince yourself that this is still a 4-punctured sphere. But you see that the asymptotic states, they're not just like usual cylinders, but they can sort of wind around the insertion point in the boundary. And there can be several parts of the sheet that hit the boundary together. So we have this non-trivial winding around the insertion points, which we don't have in flat space. And that's, from the worldsheet point of view, will come by the spectral flow automorphism. So that's the main difficulty of these correlators and why I think they have not been solved yet. And there's lots of beautiful math behind it, as I want to try to convince you in this talk. So I think it's a very worthwhile exercise to study these correlators. Okay, so before showing you how everything works in detail, let's just tell you some consequences of our work. So first of all, I already told you that the spectrally flowed correlators, they're very interesting and non-trivial, and they're both interesting from a physical and mathematical point of view. From the worldsheet point of view, if you're just interested in CFT, then they correspond to non-highest weight representations. So usually in CFT, we have some conformal highest weight representations that are annihilated by positive Virasoro generators or something of the sort, but that's not actually true here. So we have some representations on the worldsheet that are not highest weight. Because of that, the usual CFT techniques to study correlators don't really apply here. And one has to work out some new CFT techniques to get a handle on those. So your reward, if you solve that theory, in the sense that maybe you give a closed form formula for the 3-point functions. So that's one of the things we do. We give a proposal for the full 3-point function. Then in principle, you have a road to test and even derive the ADS-CFT correspondence, starting from string perturbation theory. Another very interesting feature that happens here, but doesn't happen in flat space, is that if you compute a correlator, then we know then there are some singularities in modular space of Riemann surfaces. And usually in flat space, they occur at the boundary of modular space of Riemann surfaces. So say the simplest case is that genus is 0 and n is 4, a 4-point function. Then whenever two vertex operators collide, we have some singularity. But here we actually have more singularities than that. And we have singularities of the correlator that occur in the middle of modular space, even at genus 0. So it's not entirely clear to us how to even properly define the theory as an integral over modular space. Okay, another thing is that these singularities, the presence of the singularities is related to the existence of certain holomorphic ramified covers. Namely, if I go back to this picture we had on the previous slide, the worldsheet you can think of as some 4-punctured Riemann sphere. And the boundary you can also think of a 4-punctured Riemann sphere, because there are the 4 points where the string hits the boundary. And it can happen that these winding numbers, they sort of give you ramification indices. So if there is a holomorphic covering of the worldsheet to the boundary with this given ramification indices, then it turns out there is some singularity in the correlator. So these correlators, they encode many, many things about the geometry of branch covers. And because of that, there are many connections with Hurwitz theory. Okay, so these are some teasers. But now I want to go back and start from the beginning and explain you some background. So first of all, I will only consider bosonic strings on Euclidean ADS3. The bosonic is because we are just going to study genus 0, and we don't really have to worry about any tachyons or something of the sort. And I will also make some analytic continuation to Euclidean ADS3 target space, just because it's much simpler. Otherwise, your boundary wouldn't be a Euclidean space, and your branch covers would be from some Euclidean to Lorentzian space and so on. So let's just make everything Euclidean because it's simple, and try to understand that. So the worldsheet CFT is this SL2R-WZW model, or rather it's Euclidean analytic continuation, and it possesses this SL2R affine Katz-Moody algebra symmetry. And here, just for your convenience, I wrote down what the affine Katz-Moody algebra is. You don't actually have to know that to follow the talk, but it's just the usual SL2R algebra together with some mode numbers, and there's a central extension, and the central term that appears here is just a number. The number I call K, and K here physically measures the size of ADS3 measured in units of string length. So it's a dimensionless number, which is another thing that you don't have in flat space. In flat space, there's no dimensionless number in the string. Okay, and now these winding or spectral float vertex operators, they can be constructed by using the spectral flow symmetry of the affine algebra. So I don't want to go too much into details, but this affine algebra has an automorphism that basically mixes up these mode numbers with the charges, plus and minus. And so it's an automorphism. So whenever you have some representation, you can compose with the automorphism to produce some new representation. And by that, you can abstractly define some new vertex operators that are obtained by composing with this automorphism. So let me explain you a little bit how these vertex operators look like. I can't really give you an explicit formula like in flat space. In flat space, vertex operators are just like plain waves in physics language. So there's something like e to the ikx. In this case, there's no explicit formula like that. I can just tell you in a representation theory point of way what they are. So let's start with unflowed vertex operators, where we haven't applied the spectral flow. And these are highest weight representations. So these are the sort of usual vanilla vertex operators that you know, and the string is almost point-like if you have these kind of vertex operators. So they are sort of much more like we're used to from flat space. So they are labeled, and since we're in ADS3, we label them by some SL2R spin, because there is an SL2R symmetry, and so there's some corresponding spin, just like in the SU2WCW model. But contrary to SU2, the spin is not a half integer, but rather it can be a real number, or it can be in the principal continuous series when it's a half plus IR. And so the 0 here just means it's unflowed. Then, of course, this vertex operator will need to have some insertion in the worldsheet, which I call Z, just like in flat space or something. But then we also need to say what is the boundary coordinate of this worldsheet operator. So that's something new that you shouldn't know from flat space. So this boundary coordinate, just again in the picture, is the point on the boundary where this vertex operator hits the boundary. So let me go once more back here. So there is some point on the boundary where this vertex operator hits the boundary. And if you want a more algebraic explanation, you can just abstractly, there's some SL2R spin, and this coordinate x transforms under fractional linear transformation in this x space, transforms with weight j. Or said differently, you can specify the OPE of the current with the vertex operator. The OPE is just a way of saying that this is a highest weight state, or the field corresponding to a highest weight state, because they are just simple poles. And also that's how the zero modes act. So the J0 plus acts by derivative, which means it's a translation operator in this X space. And the J03 is the dilatation operator or scaling operator. And this J0 minus is sort of a special conformal transformation. So there are sort of two coordinates here, and they're almost on the same footing. And both have an SL2R symmetry. One is the conformal SL2R symmetry in the worldsheet, and one is the spacetime SL2R symmetry. And you should perhaps also notice that, for instance, the eigenvalue of, so you want to identify these three generators of the spacetime SL2R with the conformal generators of some spacetime CFT, assuming there is something like an AD-CFT correspondence and there's a spacetime CFT. If you do that, then you find that this J is nothing else than the conformal dimension of the spacetime in the spacetime CFT. So this operator will correspond to some operator on in the boundary CFT or spacetime CFT, and its conformal dimension is this J. And I sometimes also call it H, because you will see that on the next slide. Okay, so this is sort of the unflowed vertex operator that's kind of well known in the literature. I will also tell you later more about what's known about the correlators of these guys. Okay, so now let's go to the flowed vertex operators, which are our real interest. And so now I just put this label 0. Now it's the label W, which labels the amount of spectral flow you have applied, and can be any integer, non-negative integer. If you put 0, then you're back on the previous slide. But I really want to put 1, 2, 3, and so on. And then there's still an SL2R spin that labels these representations after applying the spectral flow. But, and there's still this coordinate Z and X around. But it turns out that now you need a new quantum number to describe this operator. So that might not sound particularly obvious to you, but one way of motivating why this should be the case, without explaining you all the representation theory behind it, is that this Z transforms on the worldsheet with some weight, the worldsheet conformal weight, let me call it delta, and X transforms in the spacetime CFT under some weight with the spacetime conformal weight H. And in the unflowed sector, these two things are related. And they're related if you know the SU2WCW model, then this formula might look familiar to you. This is just a Casimir divided by this K minus dual Coxeter number. And similar formula applies here. That's for the unflowed sector. But if you go to the flowed sector, these two things become independent. And essentially one way of writing it is that there's this extra term minus WH plus K over 4W squared, I think. So, but the point is just that there are two independent quantum numbers you need to describe this operator. Another way of seeing that is I told you that this J could be either a real number or it could be in 1/2 plus IR. But of course, from a space-time point of view, you don't want your conformal weights to be in 1/2 plus IR, because in a space-time CFT, that's supposed to be a unitary CFT. And these operators will lead to space-time operators. And because of that, you don't want this H to be in 1/2 plus IR. And it's in fact independent of J in the flowed sector. So this H would be a real number, in fact, a positive real number, because it should be unitary, the CFT. And this J is still either in real numbers or in 1/2 plus IR. Okay, I'm sorry that I can't really explain that in detail because it would be sort of technical. Yeah, and you could also define these vertex operators more abstractly by giving the OPE of the currents with these vertex operators. And basically what happens is now that they have higher order poles, which reflects the fact that these are not highest weight states of the affine algebra. In fact, one of the currents, like J plus, will have a very high order pole. The pole is of order W plus 1. J3 will be a pole of order 1, like before, and J minus will have not a pole, but it's in fact regular, and it's regular up to order 1 minus W. So you sort of compensate for the fact that one current has a higher order pole by the fact that the other current has a regular OP. Okay. So, but now let's assume that we all know what these vertex operators are, and let's try to compute their correlators, and let's try to learn something about the CFT. And so in the following, I will do something very naive. In fact, I will just invoke all the symmetry, I will just impose all the symmetry constraints that we know on these correlators and see what we get. And it turns out that there's a very natural conjecture you can make what the full correlator is based on that. So what are these constraints? So there are global word identities, which just means you use the spacetime and worldsheet SL2R to fix 3 coordinates, 3 of the x's and 3 to the z's to any value you like. That's like in usual CFT, except that you have 2 copies of SL2R. Then turns out that if you go to spectral flow sector, there are also more constraints that are imposed by the presence of the affine symmetry. So these constraints you don't have in the unflowed sector, and we call them local word identities. Then there is a Knižný-Samologikov equation that is sort of a mixed word identities because, so I will explain it later, but it relates the currents and the Virasoro algebra. And because of that, that leads to some constraint on the correlator as well. And finally, for some special correlators, there might be some degenerate. Some of the spins might be chosen such that there is a null vector in the Verma module, and then you get a null vector decoupling equation. As you might know, for instance, also in Bilville theory, that gives also constraints on the correlators. So these are basically all the constraints we are aware of. There are more, but not in the form of differential equations. These are all differential equations on the correlator. And so basically now what we do is to solve these constraints case by case for many, many choices of W's. So let's say you take a 4-point function and you take the W to be 1, 2, 3, 4, whatever you want. You go to Mathematica and you input all these constraints and solve the equation and you get some result. And that we did many, many times, and we were able to find some general structure and make a conjecture what the correlator should be. Okay, and the main output will be, like, the philosophy is that you don't actually have to do some new bootstrap or something like that. All you need to know, if you know what the unflowed correlator is, and I will tell you in a second what's known about it, then there's some procedure that you can do in the form of some integral transform that puts you immediately on the flowed correlator. So you don't have to know any new, like, OPEs or something, the flowed sector, to do that. And from going here to here, like, you also don't really need new CFT input. Like, once you believe our proposal, all you need to know is about all these covering spaces and branch covers, Hurwitz numbers, and so on. All this will enter to go from here to here. So it's kind of interesting. In particular, it's also interesting, I think, that this comes out of just imposing symmetry constraints. So the affine algebra knows everything about these covering maps. All right. Okay, so let me tell you a little bit about what's known for the unfold correlators. So they are known, at least in principle. So they're as known as, for instance, the Liouville correlators are known. So that means is that there is a closed form formula for the 3-point functions, and this formula is very similar to the DOZZ formula of Liouville theorem. So this was developed mainly by Teschner in a couple of papers. There's also a notion of conformal block for the current algebra, and these are also known, at least in some short distance expansion or something, not in closed form. And then you can obtain, for instance, a 4-point function by doing a conformal block expansion and summing over all these 3-point functions. So in principle, at least the unflowed 4-point functions and even 5-point functions and so on are known. But in the following, since my focus will be really on the flowed correlators, I will just assume them to be known, and that's all we will need for this talk. But so that's basically, it's as known as in Liouville theory, I would say. Okay, so now I will just go through these constraints kind of quick and tell you what they impose. So the easiest ones are the global watered entities. The global watered entities just allow you to put 3 of these x's and z's to 3 values, and we use a standard value 0, 1, and infinity. And you can always put them at different values again by using like these SL2R invariances. So that means if you study a 3-point function on the sphere, then the x and z dependencies are just fully fixed, while for a 4-point function, you still have some cross ratios. One thing I haven't yet mentioned, I should make clear, we will just study this whole thing for the 3- and 4-point function in the sphere, just because we're not infinitely powerful. But of course, it would be nice in the future to do this for more general correlators. Okay, so that was the global watered entities. Now let's go to the much more interesting local ones. So as I've already mentioned, the presence of this affine symmetry implies that there's one additional constraint for each spectrally flowed operator that is present in the correlator. And you might be happy about this because I also told you that these spectrally flowed vertex operators depend on one more quantum number. Namely, there was the unflowed correlators where I called something like this, and the flowed correlators I called something like this. So that means like this H quantum number is basically a new one. And to solve for the dependence on this H, you need one more constraint. And that comes in the form of these local watered entities. So however, these local watered entities, they're there, but their derivation is kind of messy. And the only way I know at least how to derive them involves writing down some system of many, many equations, that many equations. And then you have to eliminate many of these equations. And in the end, you remain with just n equations. And these are the local watered entities. But from this procedure, it should be clear to you that you can't really do that in closed form for every W. Or you can maybe do if you're smart, but we were not smart enough to do that. So because of that, presently, we can only do that on a case-by-case basis for every choice of spectral flow. Is there a question? Here's someone saying something. Okay. Good. So let me just give you one example how they look like. So for instance, if you make all the W's, all the spectral flows equal to 1, so you're looking at the endpoint function here, I wrote it even for an endpoint function like this, then these local watered entities take these form. So this is just one out of n equations. And I abbreviated a little bit the notation. I dropped the j's here and the x's and the z's. I hope that's clear what I mean. And just to show you the structure a little bit, so this is an equation that is like a recursion relation in these h's, because for instance, here there's an h1 minus 1, and here there's an hi plus 1. But it's also a differential equation because we also have these x derivatives. So, and so this is the easiest of the one, and then it just gets more complicated if you increase the amount of W. Okay, there's a question in the chat. What is the conceptual idea behind the local watered entities? Okay, so the conceptual idea is that you study correlators of with one current insertion. So something like this. And I told you before that the J plus OPE with these V's is much less regular than it used to be in the unfloat. But on the other hand, the J minus OPE is much more regular than it used to be in the unfloat. So essentially, you constrain these correlators by saying this thing is something that has many high orders poles if the Z hits one of these vertex operators. But then you get many, many constraints on these correlators as well, because if you take this A to be a minus, then this has to be very, very regular if it hits these vertex operators. And because of that, you can write down all these equations that I mentioned. And it turns out that if you do that, there are n constraints that are left over. Yeah, it's sort of technical, so I didn't want to explain it in too much detail. Does that answer the question, Greg? More or less.
Yes, thank you. That was very helpful.
Thanks. Okay, so that's more or less the name of the game. So yeah, we have these ugly recursion relation things. So in order to solve them, we use some convenient trick, which is just to go to sort of Fourier basis. So we do this integral transform where we write VJHH bar as an integral transform over this y's. And then we have some vertex operator that formally depends on x, y, and z. So now I introduce a third coordinate y that is also valued in CP1 associated to this vertex operator. And you can just go back and forth between these two definitions. So this is a sort of weird vertex operator because it doesn't have definite conformal weight, neither on the world sheet nor in spacetime. So I'm not sure how physical this thing is, but it helps us a lot to solve these recursion relations or local Ward identities. And if you do that, then the recursion relation I showed on the previous slide just becomes a partial differential equation. And for instance, in the same example, but now specializing to a 4-point function, this partial differential equation looks like this. And this is just one out of 4 equations. Okay, so it seems very messy, but I will convince you in a moment that there's a nice solution. And this solution will, as I already also announced, involve these branch coverings. So let me just briefly recall what they are, and maybe I think about them in a slightly more physics way, I'm not sure. Okay, so the solution is encoded in branch coverings, and the branch cover I will just need from the 2-sphere to the 2-sphere, or CP1 to CP1, is a holomorphic map with just finitely many ramification points that I call Zi. And near these ramification points, my map gamma takes the following form. So it just means that the first W minus 1 derivatives at Zi are 0, and Zi is mapped to Xi. And these are all the ramification points. So now a very important fact is that if you choose your Xi's, Zi's, and Wi's in some random way, then you won't find a covering map. The existence of a covering map poses you n-3 constraints on the Xi's or Z and Zi's. So another way of saying that, maybe you're more familiar with this, is to say you fix your base space, which means that you fix all the Xi's and the Wi's, and then they're just a discrete number of coverings. So the Zi's are fixed, basically, up to SL2R, SL2C transformations. What's maybe slightly strange is that I will also allow the W to be 0 or 1. So if it's 0, then I could just delete it from the list because there's no condition at all, because gamma of Z, like this term is already like constant, so it's not even mapping to Xi. I can just delete it from the list. If W is 1, then there's no ramification point, but still I require that Zi is mapped to Xi. That just will make things more uniform later. Okay. So I mentioned that there is such a constraint that links X and Z. So for a 4-point function, there's just one cross ratio and there's just one constraint. And so X and Z have to be linked. And there is a single irreducible polynomial that, that shows the relation between X and Z. So the 0 locus of this polynomial is supposed to be the relation between X and Z. So let me just make a simple example to show what I mean. So for instance, if all the ramification indices, of course, they're not ramification indices, but if they're all 1, then this relation is just that the 2 cross ratios have to be the same. Because I'm talking here, I'm requiring the existence of a map from the sphere that is parameterized by the Z coordinate to the sphere that is parameterized by the X coordinate. and it's supposed to have no ramification point at all. But I'm requiring that 4 of the point 0,1 infinity is mapped to 0,1 infinity. And because of that, it is a Mobius transformation. And of course, then also X has to be mapped, sorry, Z has to be mapped to X. So that means that the 2 cross ratios have to be the same. I put some weird prefactor here. You can safely ignore it for the rest of the talk. It's just will make things more convenient later on. And of course, it's no longer polynomial because of that, but still it's convenient. Yeah, just to show you some more examples. So there's always this irreducible polynomial. So for instance, if you want to find, say, a ramification indices 2, 2, 2, 2, then it's some more complicated polynomial like this. And if you want a more math way of saying it, is the 0 locus of this polynomial, which is some subset of CP1 times CP1, is nothing else than the Hurwitz space for this situation. Okay. So this is the main mathematical input. Now let's go back to these local word identities. And let me remind you about first the global word identities, because the local ones will look very similar. So the just chiral solution of the global word identities in the unflowed sector is just given like by this. So this should be a formula that's more or less familiar. So that just says that if you have this 4-point function that depends on the axis, then there's a single undetermined function that depends on the cross ratio. And then there are some prefactors that are needed to get the correct SR2R covariance. So that's for the axis, and then there's one for the X bar, for the Z and Z bar, but let's just focus on the axis. And it turns out that the solution of this local word identities has a very similar structure in the flowed sector, but instead of these Xij's, you have to replace them by some more general object that I call generalized differences, and I call capital Xij. And this object will depend on the cross ratio X and the cross ratio Z, and on the Yi and Yj. Remember these Y's we introduced, these came in by doing this Fourier transform to turn the local word identities into differential equations. So what are these generalized differences? In fact, you can make an even slightly more general definition. You can define an Xi for every subset of 1, 2, 3, 4. And they're defined as summing these PWs, which were these polynomials that encode, whose 0 locus was the Hurwitz space. You sum them and you shift the ramification indices up or down a little bit, and you include some Yi's to it. So you're invited to decode this definition, or I can just give you some examples, then it should be clear as well. So for instance, if you take I to be the empty set, then the sum has just a single term, and the single term is just the PW itself. So that X empty set is nothing else than this polynomial, and its 0 locus of X empty set is, again, this Hurwitz space. So if you add one number, so if you make a single element set, then there will be 2 terms in this definition, and it will be a P where the 3rd index is shifted up by 1 unit, and a P where the 3rd index is shifted down by 1 unit. And for every index that you shift down, you should include a Y3 in front. Similarly, if you want to put the X1, 2, now there are 2 elements in the set, then you have a sum of 4 P's, and they're like the W1 and W2 are either shifted both up, or one is shifted down, one is shifted up, and so on. And for every shifted down, you include the corresponding Y in front. So these are the sort of important objects that seem to enter the solution. We don't have any good intuition why this is the case. But now I talked a long time about this, so let me just give you now the general result. The result is that whenever the sum of W is even, there's also a corresponding formula for odd, but let me just focus on the even case, then the following formula seems to be true. So if you compute the 4-point function of these vertex operators, and I directly wrote it in this Y basis instead of this H basis, but you can always do the integral transform to go back, then the solution looks like this. So it's exactly the same as in the unflowed sector, which I wrote here again for convenience, where you replace this Xij by the capital Xij. And the exponents are exactly the same. The only exception is that now you also need this X empty set in front. This X empty set is something where I don't know what the unflowed analog would be, probably just 1 or something like that. Yeah. So we don't have a general proof for this, but it seems to be true. We checked it in more than 1,000 examples. So we're pretty confident that this structure is the correct one. And as I said, there's also a similar formula if the sum of W is odd. Okay, and this formula is even valid for the unflowed sector. You can even put some W's to be unflowed, and then this Y, there's no longer, for instance, if W1 is 0, then the Y1 just drops out of this equation. You can check it. So in particular, if you put all the W's to 0, then this F should be the unflowed correlator. Okay, so the consistency of our proposal is kind of non-trivial, even the consistency, and it implies many intriguing identities for the polynomials PW. So that's the sort of pure math output that I was hinting at in the beginning. So for instance, one thing that happens is that this sort of generalized cross ratio that enters the unknown function, it should really behave like a cross ratio, which means that it should satisfy an identity like this. So if you do 1 minus this cross ratio, then you should again get a cross ratio, except that now the indices have been permuted around, just a different cross ratio. And that's, for instance, yeah, for the xij's, of course, this is a small xij's, this is a stupid identity, and it's clear that it holds. But in our case, this is a highly non-trivial identity. If you translate it in terms of these polynomials PW, then it will be some identity that is quadratic in the PW, and it's something like P. So there's PW, PW, like there are 3 terms like this, is 0. And some of these W's are like shifted up by 1 unit, something like this, plus E1, where this is the unit vector, and some are shifted down by 1 unit and so on. So there's some quadratic relation like this. And remember, this PW, the 0 locus, was the Hurwitz space. So this is some non-trivial relation between these polynomials defining the Hurwitz space. So it looks like the constraint coming from some Plücke embedding of a Grassmannian, but I have no idea where this is really coming from. So yeah, it's something I would like to understand very much. So if someone has an intuition where this is coming from, I'm very happy about the comment. And we have looked through the math literature, but we haven't found any sort of identities like this. And that's also not the only one. There are many identities of this sort. These PWs seem to satisfy many, many interesting things. Okay. So now let's go back to the 4-point function. We now know what the solution to the local ward identities is. But we're in fact not done with the list of constraints. We can go even further. So that is just the same formula as before. And we can ask whether we can constrain this unknown function even further. And we can, because we still haven't imposed the KZ equation, and for special values of spins, there are also null vector decoupling equations. So let's start with the KZ equation. The KZ equation comes from the fact that you can write the Virasoro tensor as a bilinear indecurrence like that. And that one, this L-1, just is the translation generator on the worldsheet. So that gives you like a Z derivative. And this thing you can also evaluate, and it will give you some X derivatives. So you can turn this thing into a differential equation. And if you do it, you get some differential equation for this unknown function f of C and Z. So here C, I call this generalized cross ratio of these capital Xij's. Now, something very surprising to us happened is that this differential equation a priori could depend on W and so on, but it turns out it doesn't depend on W. It's always the same differential equation, and it coincides with the KZ equation that you would get in the unflowed correlator. So by that, I mean, if you take the correlator where you just put all the W's to 0. So that means, yeah, in the box is that the KZ equation for the flowed correlator is just the same thing as the KZ equation for the unflowed correlator on this function f of C and Z. And this is basically the same slide, just to tell you the same thing happens for null vector equations. So for special values of spins, there are these degenerate representations, and they give rise to additional differential equations for this fc of Z. And again, these differential equations a priori could depend on W, but they don't, and they always coincide with the null vector equation that you would get in the unflowed sector. So that means, again, this is basically the same box. The null vector equation in the flowed sector reduces to the unflowed null vector equation on this f of C and Z. So if you haven't followed that, it's not so bad. I can just tell you the consequence. So the consequence is that this object satisfies exactly the same constraints as this object. And so we're very motivated to just equate them and to conjecture that this f of c and z is nothing else than the unfold correlator. A priori, there could be some non-trivial number here, some normalization. We strongly believe that this normalization is 1 because of various other consistency checks that I will tell you later. So I will immediately assume that it's 1. And now I can finally tell you what our main conjecture is. Namely, I told you in the beginning, you don't have to know anything about the correlator. It's the float correlator suffices if you know the unfloat correlator, and then I can give you a formula what the float correlator is. And here it is. So you're interested in the float correlator that depends on this v, ji, wi, xi, zi. I also put some right-moving quantities here that I haven't really emphasized before, but everything has also some right-moving analog. It's given by this integral transform. So here I wrote the integral transform. Then there are these prefactors, this x empty set, xij's that we saw in the solution of the local word identities. And the only difference now is that I replace this unknown function f, I replace with the unfloat correlator. As I said, this is in principle known. So that means also now this is in principle known. Okay, and these xij's are computable in a very efficient way. So there's, okay, Greg asks whether the integral over the yi's converges. And in general, it doesn't. It converges in exactly the same way as, for instance, in the Coulomb gas formalism for Liouville theory. So it's an integral that is only, that you have to define either by analytic continuation or you have to define in whatever twisted, so one way we used to evaluate this, we evaluated this explicitly for the 3-point function, where you know what this thing is. So it's a closed form thing, closed form integral, and we evaluate it in terms of twisted cohomology. That's one way of defining this integral. And in this case, you get some Lauricella hypergeometric function. But yeah, they don't converge absolutely, these integrals. Okay, so yeah, so we have this nice formula, and now we want to understand it a little bit more. Yeah, let me just, okay, there's another question. What is the k to infinity limit of these formulas? Yeah, that's a good question. It's very non-trivial to take this limit, and I don't really understand it very well because, I mean, there's a whole discussion how the ADS goes over to flat space. So in particular, I think very roughly speaking, but I'm not sure whether this is true in any way, this xi's should go over to some sort of celestial sphere coordinates or something like this in the flat space. Well, the problem is that these xi's are very different from the standard momenta that you have in flat space. So I'm not entirely sure how you would relate them. There's a discussion how to do this in Mellin space. In Mellin space, it seems to be fairly natural. So maybe the natural thing is to go to Mellin space here, and there you can take this limit. Yeah, so I don't have very much intelligent things to say about that. Okay, so yeah, just to show you a little bit of an example, because to not make it too abstract. So yeah, this is our formula or our conjecture. If you just plug in some simple values like w equal to 1, w1 equal to 1, 1, 0, 0, then you have these prefactors, which comes from these xij's. And then you get the unfold correlator where you put the cross ratio. Now is this sort of complicated combination that involves all the y's and the x and the z. So just to show you that everything is completely explicit. There is some further evidence for the proposal. So one thing is that this correlators, they have to enjoy bosonic symmetry. So you could just swap two operators, and of course they should be the same. And it's actually highly non-trivial if you look at our formula that this is true for the formula. And it turns out to be true, but thanks to some sort of other miraculous identities. So that passes the test, and we view it also for evidence. So as I said, like internal consistency is already a very strong requirement here. Another thing that I haven't mentioned is that there's a reflection symmetry for this model. So if this J is chosen to be in the principal continuous series, then J and 1 minus J are equivalent representations. And so the correlators, they're related by some simple transform. And so you can check that our proposal preserves the reflection symmetry in the float sector as well. Of course, you can check with some known results in the literature, but I should really say in the literature, there's not very much known. There's like the unfold sector known, and then there's some 3-point functions like 001 is known or something like this. So there's very few to compare results to compare to. Yeah, I mentioned already it's internally consistent. And one other thing that I haven't talked about at all, because this is more of a math conference or a mathematical physics conference, is that we actually went ahead and made some predictions and checks about the spacetime CFT. And there are many parts of the correlates that match with expectations about the spacetime CFT. So that's also sort of exciting, and that's part of the work in progress. One last thing I want to mention before closing is about the singularities that I already mentioned in the beginning. So usually CFT correlators just have singularities whenever two vertex operators collide, at least on a genus 0 surface. So in the present case, that would happen if Z is 0, 1, or infinity. So in this model, something else interesting can happen, namely the vertex operators can also sort of collide in space-time, which means they collide in X space. And that means you also have singularities in X space whenever X is 0, 1, or infinity for this 4-point function. But it turns out that there are many, many more singularities, and they occur somewhere in the middle of moduli space. And they occur whenever one of these PWs is 0. So if you're sitting on the 0 locus. It doesn't have to be exactly PW, it can be PW shifted up or down by a little bit, where EI are the unit vectors. So these are like many, many equations for which this can be true. Like one, okay, let me just go once more back here. I can show you where one of them comes from. That's quite easy. So here you have this X empty set prefactor. And I told you X empty set is nothing else than this PW itself. So whenever you're sitting on the 0 locus of PW, this thing will manifestly be singular. And the 0 locus of PW is the Hurwitz space. And that occurs like fixing X, for instance, it occurs somewhere in the middle of moduli, Z moduli space. Okay, so it was explained partially by Maldus and Oguri what the physical meaning of that is, and we analyzed much more in detail where all these singularities happen. So in particular, for instance, in the example that I showed on the previous slide, where you have these two W's being 1 and the other W's being 0, you have singularities whenever Z is X or when this equation is satisfied. Some of them you only see after doing the integral transform over Y again. Yeah, so that's another sort of curious feature of this model, and we don't actually really know what this implies for the string, because it means that I think that the compactification of moduli space perhaps has to be chosen differently than the standard string. I'm not entirely sure, but I mean, this integrand of string theory has more singularities than you're used to. Okay, so I'm basically done. So let me summarize what we have done. So I told you that we have a full conjectural solution of the worldsheet theories for strings on ADS3 with the inclusion of spectral flow. So far, we have just looked on it on the sphere and for at most 4 points. So, but the main lesson that we learned is that whenever you know all the unflowed correlators, then there's sort of a integral transform. That integral transform just involves geometry, essentially. It doesn't involve any sort of complicated functions like you're used to in the DOZZ formula or something like this. It's just like geometry, basically, and you get the flowed correlators out of it. So, of course, I would be very happy if this is true in general for higher genus, higher points, and I think something like this is probably true. And we somehow have scratched only some tip of the iceberg, and we don't really know what the structure behind it is. In particular, one output was also that there are sort of all these mysterious, or at least mysterious to us, identities for Hurwitz spaces. So for these 0 locuses that define the Hurwitz space. And yeah, the final thing that I have showed you is that the worldsheet correlators have this strange singularity structure. So they have many more singularities in the ZIs than you would naively expect. With that, I thank you very much for your attention, and I'm happy to answer any question you might have. Thank you very much.
Thanks a lot, Lorenz. Are there questions? I don't see any raised hands. Okay, here we go, Andrew.
Hi, yeah, great talk. I was just wondering if you could say a word about one of the ADS CFT checks you mentioned.
Yeah, sure. Okay, so the check is basically that if you compute so what you can do is, because of the singularities, you know, for instance, in flat space, the presence of the singularities implies that you have poles in the amplitude. So for instance, if you compute the Veneziano amplitude, it has poles. And the reason for these poles is basically that there are singularities in the moduli space. And so what you can do is, we presently don't know how to compute some integral over moduli space of Riemann surfaces for these complicated 4-point functions, but we can at least see what is implied by the presence of the singularities. And they imply that you have some poles in the correlator of the dual CFT. And near the pole, you can compute the residue of what the residue should be. And if you compute the residue, you find a residue that we recognize. It's a theory that we recognize. And the theory is a symmetric orbifold of basically free boson with a screening charge. And then there's some, and let me just write times x. X is the CFT that describes like the internal space of the compactification. You have something like ADS 3 times x. And the symmetric orbifold just means you take n copies of this and divide out by the symmetric group action. And here there are twisted sectors. The twisted sectors are mapped to these ramification indices, or these spectral flow indices W. And what these correlators become are the correlators of these twisted sector, these twist fields in this orbifold. And you get, and this free boson is basically what remains from the ADS3 factor, because there are some two directions that are thrown out by physical state conditions. So you remain with one boson, roughly speaking. And you can check that these correlators land exactly on the correlators of this symmetric orbifold, at least near the singularities, and including all the normalization and so on. So that is kind of striking to us, and is a nice check. Well, yeah, so we're not proposing that this is the dual CFT, but at least it's the CFT that describes all the singular parts of the correlator. Yeah.
Cool, thanks.
I have a couple of questions. Perhaps one is about language, but before. So in the examples that you showed, that you could make it very explicit, these new singularities that appear, they are rational. So do you know, in principle, since you have the solutions to these integral equations, do you know if you can find singularities that are not, or correlators that are not rational functions?
Well, after doing the integral transform,
Yeah.
the correlators won't be rational. Like these won't be rational. These will be some complicated hypergeometric function. All these integrals are of hypergeometric type. But it's true that the conditions for the singularity, they're always rational. So are you asking whether the PW is always rational?
Yeah. So I wonder if you can see, for example, dilogarithms of the 4-point functions.
Not at tree level. I think if you go to loop level or something, it's likely that something like that will appear, but not at tree level. Yeah, so this just describes the position of the singularity in moduli space. It's not something fancy, and it should be like some single valued object. It shouldn't be like have several branches or something.
I see more raised hands, so I can bug you for something about language. So when you said that these are non-highest weight representations, so I wonder what does it actually mean? I understand that these vectors that you were looking at are not highest weights. They're not primary for that particular representation of the affine algebra.
Okay, let me just write you down what what the condition is. So usually you would say something like this, like let's say phi is our highest weight state. Then this would be 0 for m bigger than 0, and a is plus minus or 3. And we would also impose like the 0 mode, J0 minus phi is 0, let's say. That you would agree, and then the 3, the Cartan generator would be the spin J. So that would be the unflowed situation in terms of representation. And if you want to go to the flowed sector, you would impose something like this. that the plus generator on this is only 0 if m is bigger than w. So you have to make it very positive to get 0. The J03 on the phi gives you h phi. And the J, and positive modes annihilated. Like this is 0 for m bigger than 0. And for the minus guy, you have to not go very far, even negative mode already annihilated. Sorry, this is m bigger and equal minus 1 w. So the equal is because it's also here the 0 mode annihilated.
Okay. So
you see it's sort of a twisted version of a highest weight condition.
But yeah, so but the J0 still acts diagonally and
yes, yeah, there's another subtlety because of this x, presence of the x. So basically the x, like this guy.
So I'm disregarding anything on the boundary. Yeah, I'm disregarding. I'm disregarding everything of the boundary.
Yeah, I'm just pointing out that there, like the operator state correspondence that you're used to, there are 2 coordinates now associated to it. So it's at x equal to 0 and z equal to 0. So that's the sort of representation that you have at x equal to 0. Correct. And if you want some field that sits at non-trivial x and non-trivial z, then this condition will be modified. And there will be some x dependencies as well. So
still okay. Okay. Thanks.
Yeah.
So if there are no more questions, perhaps we should go for another round of applause. Thank you.
Thank you.